So this is for the Thursday. I have an old air launcher that the Cantina bought, and we spent like 85 bucks on it because the old ones were getting all torn up. Well, then we used it last year, worked okay, and then this year it just leaks everywhere. So first hour was a disaster as usual. Second hour, I used an old launcher and it's all zip tied up and it's all falling apart, but it still works. And that worked beautifully. And third, so we got 2 launches in, and then third hour we did 2 launches and picked the best one. So we had success on the air rockets. And so we'll talk about that as soon as I can open this up and hope. And then yesterday afternoon, I messed with this for a long time, kept resetting my iPad, and finally I got it to share. So here's the moment of truth here. Having some big technical issues lately. And moment of truth. Yay. Okay. So things are working again. Okay. So we're Thursday, class number 11. So today we're doing this. We're talking about this mostly. And then at the end, we'll start talking a little more about damped oscillations. So a little look ahead. We'll wrap up damped oscillations tomorrow. And we'll do a stringless pendulum here later on. And then tomorrow we'll get back into vectors. And we're pretty much going to stay on vectors for tomorrow, Monday, maybe Tuesday next week. And then we're into what's next. I think after that, we may get into calculus, into derivatives. And I don't know if we'll even get all 11 sheets done in packet 4. I'm always more optimistic when I first put the packet together. All right, so let me stop this sharing. Now I know that works. And let me share another screen. This one. So here is the, share. Here is, okay. I'm not sure, I haven't seen these yet. I'm seeing them, they're 7 seconds long, so not much happens here. Let's see what happened here. This is me on the west lawn. I guess you guys can see that. Me on the west lawn, getting ready to launch. This is during third hour, getting ready to launch the rocket there. I got a pump. I turned it on, and here we go. And then there's about 4 students. You can't see them. They're to the south. Timothy did this one. Maybe he zoomed out. I don't know. They're to the south, and they have the altitude guns. So they're getting ready to look at the angle. And then I have a bunch of students behind me with timers. They're going to time the total time of flight. And then I have a couple of students like Timothy here that filmed it. Let's see what happens. Oh, there he goes. All right, so he has it in super slow motion. Let's rewind that a little bit. There we go. Look at this. So there it is taking off. And we're looking at that. Unfortunately, my time on my scale doesn't go to it only goes to the nearest hundredth of a second. So that blows my idea. So there we are, just launching. And there's 0.04. Oh, no. It only goes to the nearest second. This is terrible. It's a great film, but it's a terrible timer. So because look, there it is at 0.04, at 4 seconds. And then by the time we get to 5 seconds, it's out of frame. Well, shoot. Okay, so there it is, slow motion though. He did what he's supposed to do. He probably needed to stand back further. We'll do it again in the morning. Hold on, let me kill this one. Let me share the other screen. Okay. I got another one here. This may be better. This is probably the second launch. Share that one. Okay, now let's see what happens. So yeah, he's further back. All right, here we go. This is 26 seconds long. See if I can blow it up for you. Okay, ready? Here we go. 3, 2. Okay, you can't count down because it's a pump, and so whenever it launches, it pops, and so whenever it pops, it pops. Here we go, super slow motion. Oh, there. Oh, we got in a couple of frames there. All right, so we can do some. Except I don't know what the heights are. Okay, hold on. There it goes, and it went up. It went up really high. That thing launched at about 60 miles an hour. That's pretty fast, and that's all we have on that one. Okay, but that might have a little bit of useful information. All right, I got excited here because there wasn't much wind, and so that really was some of the best launches I've ever had. Be honest with you. And we got some really good, consistent data. Okay, so we're going to use the data from so get out your 4.3. We're not going to end up filling it all out. That's okay. We'll fill out parts of it. That happens sometimes. But we're going to look at the data from, let's see, second hour. So so the 4 gunners, the 4 people that were using altitude finders, they were 100 feet away. Remember, this thing, here's the setup here. So I had 4 people that were 100 feet away over here, and they were doing line of sight. And then they had to come to a consensus as to what the best angle was. They have these little guns that measure angle. And then they were 100 feet away. We measured 100 feet here. And then there's a lot of people standing behind me that were doing timing. And so we used their times. And then we had a couple people filming. So that was the setup. Okay. So here's the people that were brave enough to give me what that really felt good about it. They gave me these times in second hour, these TOWs. Now that's total time of flight. That's all the way to the apex and then all the way back down. But there is definite error in this data. The error here is plus or minus 0.30 seconds, and that's being optimistic because you being a high school student, you have pretty good reaction times. Even that is about point. We did this when we took the ruler and we dropped it, the meter stick, we caught it. We actually measured quantitatively what your reaction times were. And at best, they were 0.15. Mine's 0.20. Yours are 0.15 seconds. So you have a delay in your eyes see it, and then you finally hit the start button to when it lands, your eyes see it land, and you hit the start button, you hit the stop button. So there's a 0.15 delay both times. So we add them up. You add up your error. So there's 0.30 is that's being conservative. That's my error on these times. So that means that the 10th position is the first iffy. So it's the last SIGI. So we have 2 SIGs though, and 2 significant figures is okay for high school. So our median, we got lazy and just did the median. We're going to use that for our TOW. That's the median. Having 5 times is good. And then this was our angle, and this is plus or minus about 4 degrees. So that still puts you at 2 SIGIs. So there's 2 SIGIs in both cases. Okay. Now, so now we're going to apply these to these equations. So get out your calculators here. These are our green equations. Let's do the easy one first. And that's the green here. It's the finding the launch velocity using half tau. It's half tau because we make the assumption that the rocket going up is the same amount of time as the rocket coming back down. And that's assuming that air drag is not a huge thing. The rocket's fairly streamlined. There are some fins on it, but it's pretty streamlined. And there were no updrafts or downdrafts. So that's really good. I mean, that thing came down. I wish he'd shown the whole thing. That thing came down probably 6-7 feet away from the launch pad. That just doesn't happen. About half the time it comes down, hits my truck. A lot of times it comes down like way away, and then and then you know you've got updraft, so you know it's bogus. But this is probably some of the best data I've ever had. Okay, so punch in your, once again, the average time was 5.2 seconds, the median time. So punch 5.2 seconds in for this. And then now, wait a minute. Don't use 9.81 for your G. It wouldn't hurt here, except that I want to use both methods. And so because we used 100 feet here for our delta X, we have to do this in English units, and that's 100 plus or minus 1 foot. So we have 3 siggies there. It's overkill on that. G is for English system. G is 32.2 to go 1 sig fig beyond what we need to do, and that's feet. That is feet per second squared. And theta was, according to second hour, theta was 50 degrees. So the reason why we have to keep this in G as 32.2 is because I want to compare it to the other V launch. So 32.2 feet per second squared. And our tau was 5.2 seconds, total time of flight. Okay, so punch that in to your calculators for the tau version, for the half tau version, we call that, and then the angle version. And let's see what we get. I'm going to give you a minute to do that. While you're doing that, I'm going to get some water. Okay, so go ahead, punch that in, and I'll be back. I'm going to put pause so the people at home don't sit and wait. I'll pause recording for a second. Okay, so we're back now. What do you guys get for your V launch with the half tau method?
I got 53.3.
You got about 53. Okay, so V launch is 53 to 2 siggies, right? Oh, is that feet per second?
Yeah.
Okay,
Feet per second.
yeah. We converted it to miles per hour. So I want it in miles per hour. And so we got to do a quick unit analysis. Remember, there's 5,280 feet in a mile. And of course, 3,600 seconds in an hour. So what is V launch? I need V launch both ways. V launch using both methods. This will be the half tau method, and this will be the angle method in miles per hour. What do we get? Anybody jump in there? Anybody got it? You got a calculator? Remember, the rule I have is if you pipe up and say something every time you jump in there, you get a zoom point. Now, with a maximum of 3 zoom points a session. Let's see. I'm just telling you, they got 57 miles an hour. Now, they use 32, not 32.2, but they got 57 miles per hour. That's for using the half tau method. Right? You guys with me? You guys here? You awake? feel like I'm getting the silent treatment. I feel like I'm in first hour. Okay. What'd you guys get for the using the angle method in miles per hour? I'll pause recording so we're not rushed. 59 is what they got. 59. Now check to make sure you're getting that, because, you know, on the test, these problems are on the test. You want to make sure you know how to do them. And on the test, it asks you to do it in miles per hour at the end. So 57 miles per hour using the half tau method. And just to show you, that is what they got. That's what second hour got. And then 59 miles per hour using the angle method. It's I prefer the angle method because of the not being able to give a countdown on the launch. You know, I can't say 3, 2, 1, go. If I could, I would go with the timing. Anyway, so and the rocket slows down when it reaches the apex. It stops right temporarily, and then for just a half a second, then it turns around. So it's going pretty slow, and that's been very consistent all morning. Well, all morning, 2 hours. For 4 launches, they were very consistent. Well, now we have to find percent difference in the two methods. If you ever use 2, 3 methods, you always got to find the percent difference. I noticed I didn't say percent error, because in a percent error, there is a known quantity, but we do not know what the launch velocity is of this rocket, okay, this rocket launcher. So, sorry, I'm moving that out the way. There we go. So we're going to use just percent difference, which means you get 2 values in an experiment. You don't know which one's right. Okay, in that case, we take the difference of the 2. So it'll be 59. And the units don't matter here because the units cancel anyway. It's just numbers. So 59 minus 57, it's absolute value. It could be either way. Divided by the average, 58. And so that's the average. And that whole thing is times 100. And so it looks like we have 2 divided by 58, or 200 divided by 58. So it looks like we're going to get, what is that, 3%? What is 2 divided by 2? Okay.
3.44 or 3.45.
About 3.5. So that's about a 3.5% error, which is good for high school. That's also good. Oh, that's not an error. That's a difference. But if you're trying to, if you know the 2 methods should give you the same value, theoretically, 3.5% is how far you're off. And that's really good. First hour, we'll try and beat it tomorrow morning, but we'll see. Okay. So the next thing we did in class was I had them go to the board and do, well, second hour, I gave it to them as homework. I did every hour different this morning because I got thrown off because, third hour had a fire drill, but I got thrown off because the launch didn't work in first hour. So I had to come back in and punt and come up with this stuff. So anyway, it's going to be a mess tomorrow, but you're still the official. You're the official, record of what happened in class. So I think let's go ahead and might as well do this. Yeah. Let's do it this way. So let's go ahead. You have this on 4.3 at the back. Like I said, we're not filling the whole thing in, but we got to definitely do these. And then write in up here, write in your values. Like, go ahead and okay. So we said we said 57 for tau. Okay. So you'd plug in using tau 1. We said 57 miles per hour, and then we said 59 miles per hour for that one. And the percent difference, we got 3.5%. And I don't care, but we're not doing those. Okay. So now what I want you to do to finish this sheet up is to going to the board, and I'm not going to try the breakout rooms here, because that doesn't play very well when you do that on a recording. So instead, so all those that are watching this tape, we want you to work 1, 2, and 3 at the bottom, some practice at this. You'll get more practice with the practice problems. There's 2 of those in the practice problems. But I want you to try it on your own. I'm going to hit pause so you don't have to worry about speed. You're just going to get it done. So I'll hit pause and go ahead and work on your own 1, 2, and 3. Same thing we just did, just different numbers. And so pause recording. All right, so on the recording here, you can see all the work we've done. Hopefully your did work too. And you get about a 5% difference with that data. That's the kind of problems you'll see for launch equations. Okay, good. Now, the last thing I want to do today in the next 16 minutes is I want to talk about damping. And we mentioned damping last time, but let's see. All right, so here's what we did. I'll show you what this is the actual data from third hour, and about that time the fire alarm went off. Okay. I'm surprised these bureaucrats don't make us do fire drills on Zooming. Regulation, ASCII, regulation. All right, so I'm going to show you this. So this is, for years, I have this pendulum in the room, and it's really good pendulum. It's big, but the thing is, it doesn't damp very much. And so I would make the kids show the damping, and it took forever. So they had to do all these oscillations, 20 oscillations, and that's just cruel. So I have this, I bought this stringless, it's called a stringless pendulum. And so you put a ball here. Oh, hello. It wasn't level. It's got to be, that's going to be a problem here. It's got to be level. Oh, you would go behind the, okay. I've got to go get the ball. Maybe I got another ball. I don't want to have to, when you get to be 61, you don't like to bend over and pick stuff up because it hurts. Stiff back, Okay, so here we go. This time I'll try and hold it level. I need to put a level on here. But what I did was, so we're going to measure this. We're going to plot this. But what I did was I taped a meter stick to it. So right here, this is called the ground state, where that ball is right now. That's the ground state, the lowest possible energy state. So I put that as 50 centimeters. And then this thing goes X-wise, goes 25 centimeters this way, 25 centimeters this way. Okay. And so I'll demonstrate what we did, then we'll use our data, because I don't think I can hold it steady. I need to put it on a table, but oh well. So this thing, what it does is it goes back and forth like that. Ah! All right, try it again. I'm cheating. You do this. Oh, geez. Trying to compensate for not being level. Okay, it does that. Okay. That's actually better than that marble. Oh, well. So then, okay, now let me go back to sharing the screen. So then we take that and we collect our data. So they timed it. I had them all time it for 5 oscillations. We did five cycles. Okay. And they timed it, and they got a bunch of them were timing it, and we came up with an average of about 12 seconds. Okay, to 2 SIGGIs for those 5 oscillations. It started off 25 on the X direction. It started off 25 centimeters from equilibrium, from the ground state. And by the time it had gone through 5 oscillations, it was 8 centimeters. Okay. So then about that time, the fire alarm went off. So here we are. Let's go ahead and finish. Let's go ahead and I don't want to get you too far ahead. Second hour's already done this. First hour's already done this because they had no other choice. Anyway, so let's get some of this data done. I'll tell you what we'll do. We'll see. I'll just go until I run out of time. Okay, we got 11 minutes. So to find the period, it is 12 seconds divided by 5 cycles. So seconds per cycle, 12 divided by 5 is 2.4. So it's 2.4 seconds per cycle. Just seconds. You could say seconds per oscillation, but just say seconds. Okay, so we need to plot this. And we need to plot, the thing is, this time it is an oscillation. We need to plot 5 cycles of this oscillation. So you'll need a ruler, okay, or a straight edge or something. Because I don't want this really can't be slop. It's just going to be gobbledygook, 4th grader stuff if you don't use a ruler. All right, so that's my time axis, and then my x-axis, and we're starting off at 25 centimeter. We're going 12 seconds total, so let's get that out there. I'll call that, lay it out there. 1, 2 seconds, 3 seconds, 5, 6, 7, 8, 9, 10. I'll probably go ahead and eventually get put this on. I'm turning this into a worksheet, but it won't be ready this year. So right now it's just notes. Okay, and then there's 12. Okay, and then I start off at 25 centimeters, end up at 8 centimeters. So 5, 10, 15, 20, 25. 25 centimeters. And then negative 25, 1, 5, 10, 15, 20, negative 25. And that's centimeters, and that's seconds. Okay. You hear Pepper crying down there. She's on what's up here with me. I fed her. Now okay, so now we have to get our envelope. Now the thing is, the envelope started off at 25 centimeters. It ended up at 8 centimeters. So here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I'm at 8 centimeters, which is right here and right here. So now I need to take my ruler and connect up with a dashed line. Here we go, with a dashed line. This is my damping envelope. My oscillations have to stay in there. And then that's the top part of it. Here's the bottom part. Okay. So inside that envelope, I've got to draw my 5 oscillations. Now we know it's cosine. And now I got to put my envelope. That's my amplitude envelope. Now I got to put my time envelopes on there, my time constraints. So let's see, it's 2.4 seconds per oscillation. So you see, this is called scaffolding. I'm scaffolding in, because now it's not going to be so easy. I just don't go wah, 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 wah. I've got to actually, so 2.4, 4.8, is the next one. And then 4.8. So we go, let's see, 4.8 plus 2.4. So now the next one's 7.2. 1, 2, 3, 4, 5, 6, 7. 7.2. And then plus 7.2 plus 2.4, 9.6 is the next one. 8, 9, 9.6 right there. And then the last one is at 12. So my every oscillation has to fit inside its little envelopes, temporal and length. So I'll go blue here for my oscillation. And so you start up here, and then I know that within 2.4 seconds, I'm back where I was, but not with the same amplitude. Notice on this, the frequency doesn't change. Just the wavelength doesn't change, just the amplitude. Like if I'm yelling at you, hey man, get me some Chick-fil-A at lunch. It's not that like my frequency, like all of a sudden the pitch doesn't go up where you hear, hey man, you don't, or hey man, you don't, it doesn't change the frequency or the pitch, but it's hey man, you lose your volume. And that's what's happening here. I'm losing my volume. And then, so I end up back at that same maximum altitude, not altitude, the maximum oscillation. And then halfway between, I'm at the other side, of course. So I'll put a blue dot there, halfway. And then you want to put your points of inflection, right? And that's halfway between those. So every quarter, there's a point of inflection, negative, positive. Now see, I'm forcing myself to do this right, to not get off and not get sloppy. That's what scaffolding does. It forces you to not be sloppy. It's really easy to be sloppy when the amplitude is changing. Okay, so now what I do is I only do half these at a time. I do the upsurge. I guess I'm left-handed, so I do the upsurge first to keep myself on as flat, maximum, flat, flat, maximum, flat. Then I do the downs. It's not so easy for me. Flat, 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 maximum, flat, maximum, flat. Okay. This is all called damping. Maximum, flat, maximum, flat. Okay. So there it is. That's the ball on a stringless pendulum going back and forth and losing its altitude. Now we only got a couple minutes. So let me say this. This is, yes, it's called a damping envelope. And this is linear. The thing is, it's nice and convenient for us to use linear damping envelopes. This is the introductory class. In reality, linear damping envelopes that I know of don't really exist. Real envelopes, which I will put examples in the comments, real envelopes are natural logarithms. They're E function. You know, you learn the E function. You've heard of half-life and things like that. Those are E functions. Things tend to drop off more like this. I have a picture of it. I mean, I drew it. Where was it? It was first hour I was drawing this. Now I cannot find it. Oh well. I'll show that in the anyway. Where did I put that thing? Anyway, I did a pretty good job, I must say. Hold on one second. There it is. There it is. Okay, so that nope. That's the one we did in first hour. Oh, come on. Nope. Anyway, maybe I erased it, but it's in there somewhere. But I'll show you. So, like, last thing. So, like car shock absorbers, they are they are damped. So your shocks on your car, you have to go in and get them adjusted sometimes, because sometimes they're under damped, sometimes they're over damped. If they over damp them, like if you ride a Forerunners tend to over damp their shocks. So because people that drive Forerunners, my son had a Forerunner, hated it because you really feel the road. He liked that. I don't. I drove a Pilot, and on a Nissan Pilot, Honda, on a Honda Pilot, they were under damped so that when you hit, so you kind of have a cushion that gives you cushion. You'll see people on those heavy Chevys, they under damp them and then they go down the street and they want it to go bong, bong, bong. So that's an example of damping in a car. But any kind of spring has its own damping. Some you can adjust, some that just all springs come with them. All pendulums come with them. Anything now, it doesn't, as a kid asked once, does electron come with the damping? No. Electrons will spit out energy, as we see. That's where we see light, but they come in quanta. So electrons don't. They spit out quanta of energy, like at certain levels. So it's not, and it's frequencies they're spitting out. So that's a different ball game. But for macroscopic things, points, they tend to that oscillate. They always damps. Okay, so enough. That's enough for today. Look in the comments for more information on that. We got to move on. Tomorrow we're getting into vectors again, and we'll hit vectors pretty hard. All right. Any questions before we go? I'll take a quick screenshot of all your names here. Michael, you still need to give yourself an icon. Looks like everybody else has one. All right. I'll see you guys. Tomorrow's Friday. Woo! Bye.